Hello, my name is JMeyers and this is my KI2 presentation. I'm currently in all three junior level courses, ECE 311, ECE 331, and ECE 341. And today we're going to be looking at the audio amplifier and speaker. So initially what can be said is that this is an LTI based system. The first stage here is for gain and the second stage is for regulating the output impedance, the R load. And what we can say is that this is an LTI, the MOSFETs are linear components, and the input voltage, along with the bias, which we will get into, will look like the same thing as the V out, but it will be attenuated or amplified by the magnitude of the frequency response at that frequency, and there will be a phase shift which depends on the phase of the frequency response at the frequency of the sinusoid. And we can analyze this linearly by using Fourier transforms, and the magnitudes are the same because of a property of Fourier transforms, which is conjugate symmetry, and based on the fact that the impulse response of the input is real. And if we move over here, we can see that there is not only an amplitude change, but also a phase shift associated with our V in and V out of the system at 1 kilohertz. We can see based from the last slide that there is, based on the 10 millivolt input amplitude, peak to peak, we can see that here it has a response at the 1 kilohertz frequency, which is the frequency response that we were looking at in the last slide here. And we can also see here that this is the bias voltage going here, initial bias voltage, which we will get into. But this is, as you can see, linear in nature, and we can tell that because here is a nonlinear graph. And what we can say about this is that if the system LTI frequency omega naught goes in and comes out differently, then the system is either nonlinear or it's not time invariant or both. But nothing changes in the system over time since MOSFETs are a linear component, so the system must be nonlinear in these cases. And this is because an amplitude becomes too large and small signal analysis is no longer valid, so nonlinearity creates these harmonics. And so we can see that example over here where the input amplitude is increased to 200 millivolts. And what we call this is distortion, actually. And if a nonlinear component omega naught goes in with an x of t input signal, it can come out as y of t. And if we end up squaring that or cubing that initial input signal, we can see that it will create a harmonic of that exponential value and then that of the original. And the system always does this distortion. So what you're seeing here is this harmonic distortion. The VB no longer reflects the true VB input because we have this spillage from all these harmonic distortions which are compounding down through each individual one of these frequencies that we can see. And so from this point we can ask, how can we tell if these harmonics are solely nonlinear or if they are linear? And we can decide that by looking at the V output And we can see here that, so here the input signal will not be a pure sinusoid unless the base emitter voltage, VBE, has a biased voltage greater than the 0.7 volts needed. What we can see here is that since we are losing the negative side of the output, that shows that there's more than one harmonic because it's not a perfect sinusoid. And now we're going to be talking about the electromagnetics side of things. Now, in the amplifier section, really the only electromagnetics that is relevant is that MOSFETs do have a particular capacitance that acts parasitically, but more so we're going to be discussing the speaker side of things. Now, the speaker has an electromagnet and a permanent magnet. We can see the permanent magnet here, and then the electromagnetic here in the middle with this core that can be made of a particular type of material. Well, both of these can be made from different materials, and we're typically wanting materials that are a material with a very low distortion and low hysteresis for the electromagnet, and then we're wanting a very high distortion and high hysteresis rate for the permanent magnet. Reason why this is because we're trying to have the electromagnet vibrate in this airfield here as the output signal comes, and the purpose of the coil is that it carries a current through it, and the coil behaves like a permanent magnet, which it can reverse the direction of the current in the coil, which flips the poles of the magnet. And when this electromagnet moves back and forth, it is attracted and repelled by the permanent magnets on the outside, causing it to vibrate back and forth. So with that exchange of the output voltage going through this coil, we hear the mechanical energy being translated into the air and out through the speaker. And that concludes my KI presentation. Thank you very much, and this is the best that I could do in the time that I was allotted. Thank you.